one application of Taylor series and Maclaurin series that we can see in Calc B is helping us compute difficult integrals. And when I say difficult integrals, I mean integrals or functions in which we don't know their antiderivative. And when I say we don't know, I mean the math community as a whole. So for example, one of these integrals we talked about before was just the indefinite integral of e to the minus x squared. And as joked around in class before, I said, if you can come up with a closed form representation of this antiderivative, meaning in terms of functions like exponentials, sines, cosines, logarithms, etc., you could probably make a lot of money. Well, but in this case, what we're going to do is try to find the Taylor series for e to the minus x squared, and then integrate that instead. So first, let's just find the Taylor series or Maclaurin series for e to the minus x squared. And we can do this using our stenciling idea. So if you remember, e to the x has a Taylor series or Maclaurin series. That's the series from n equals 0 to infinity of x to the n all over n factorial. And if we just stencilify this, anywhere there's an x, we can just replace it with open parentheses. And all we need to do is effectively just put in this minus x squared into those blue parentheses. So if we go ahead and do that, we get a Maclaurin series for e to the minus x squared. Okay, let's do a little bit of algebra to clean this up. And again, the reason I want to do a little bit of algebra here is just so when we go ahead and find its antiderivative of this Maclaurin series, we don't have to worry about as many chain rules or u subs and things of that nature. So if we do some algebra, we see that within this term, we have the product of a minus 1 and an x squared, all being raised to the same power, so we could split that apart. So this would be minus 1 to the n times an x to the 2n power, all over n factorial. And you know what? We can go ahead and substitute inside of our integral that e minus x squared term for its Taylor series. So let's go ahead and do that now. So subbing in for e to the minus x squared, we have its Taylor series that we just found. And what's nice about this is, well, whenever we are integrating these power series, we're integrating with respect to x. And again, like we've seen for power series, what that effectively means is we only have to do an antiderivative power rule, because nothing else inside of these infinite series have any x dependence. So if we just go ahead and integrate that x to the 2n term, we'll get a minus 1 to the n all over that n factorial that was there before. Now doing the antiderivative power rule, we get an x to the 2n plus 1. If I can get that plus 1 in there. And we divide that by a 2n plus 1 as well. And now, since this is, of course, a indefinite integral, we get to tack on a plus c. So, we weren't able to integrate e to the minus x squared by itself, but we can surely integrate its Taylor series representation. So a couple ways we could think about this is this antiderivative we found in infinite series form through its Taylor series. Well, if we really wanted to do something with this, we could use maybe the first 5, first 10, first 20 terms to give us a good approximation to whatever the true antiderivative is of e to the minus x squared. The other way to think about this is if we can find a function whose Taylor series is this series that we found from integrating, we would know the antiderivative of e to the minus x squared.